As for techniques for solving the average problems we've been working on, so I'll try to help. I think it's the more difficult question is the one that takes the forms of giving you all the numbers that make up the average, but except for the weights of different things and making you figure out the weights from knowing the raw numbers and also the final conclusion, the total average, the overall average. And that can be tricky, but not too tricky for us, I think. And it's always good to go back to basics. And so I've written there the basic definition of the average, that an average is always a sum of some group of things divided by the count of those things. That's what it means, and that's simple stuff that you've known for a long time. But I always find it's productive to go back to definitions to solve any sort of problem. It was one of the problems we had on the review quiz. 2 tests, an average somewhere in between, as averages always are, that the final average not directly in the middle of the 2 items. So it's not a straightforward average problem. There's some weights involved, and your challenge is to figure out what those weights are. Now, algebra will always help you, and if you can set up a proper equation, if you handle the tools of algebra correctly, probably you do know how to do that, then you can always solve the problem. So I can show you how to do things that way. Algebra has to give proper names to things, so we can say we've got T1 and T2 for the first 2 tests, and they're associated with weight 1 and weight 2. We have 2 things we don't know, but from this we can pull 2 equations, and that's a positive situation. 2 things we do know, 2 things we don't know. We can reduce that all to the situation of knowledge. We can know what they all are. The useful equation is that we know whatever the weights are, they've got to add up to 100%. So changing that to decimal versions, it's all got to add up to 1, the whole, the totality of the weights. So W1 plus W2, whatever they are, adds up to 1. That'll be useful because then we know how to substitute one for the other. We can end up with finally an equation with just one unknown, and that we'll be able to solve. So the second equation is more like the average situation. If we add together T1 and T2 and divide them by the numbers, the amounts in the group, then we'll get the OA, the overall average. We have to consider the weights, so we'll have to multiply T1 by its weight in the whole, and we'll have to multiply T2 by its weight in the whole. And then the dividing is easy. We're just dividing things by 1, which doesn't change the number. But it's one whole average. So what's left here is simply to fill in the meanings for the numbers, and that reduces it to an algebra problem, which I think you can solve on your own. The equation is the same. It simply substitutes what we know already for the variables when we can, leaving the 2 unknowns that we've got to discover to add up to 1. That is, they're together the weights for the whole average problem. We can make a simple algebra move to define weight 1 in terms of weight 2, and then rewrite the equation in its most advanced form with as much as possible filled in, and then fill in one more step, reduce it to 1 variable. It would look like that, which would allow you to solve for W2. I'm sure your algebra techniques are good enough to do that. If not, find some help to refresh your memory and how that works. This is the way people have been solving these problems for centuries. The good thing about algebra is that it's a standard method. It's fairly precise and secure. If you don't make mistaken algebra techniques, you'll get to the right answer. You can always practice up and get better at algebraic techniques if you're not safe and secure with them already. The bad thing is that you will often do things that you don't quite know what you're doing. You're just following the procedures. You don't know what quantities you're dealing with. What does that equation mean? What sort of truth is it expressing? That's somewhat lost by this method. But through going through a few steps without really understanding what you're doing in terms of how are you handling the problem, then if you're willing to go through that murky, clouded part of the problem, you can get safely to the right answer. I much prefer knowing what I'm doing and understanding how my solving the problem relates to the way algebra, or averages rather, work. I like the balance method for figuring out averages and solving problems, and it comes from a property of scales and balances that if you have, as I have crudely here drawn the two arms or branches of a scale, it's resting on what we call the fulcrum. It is teetering back and forth on that black triangle in the center. If you hang two weights off the ends, that you can make it even by putting the fulcrum in the right place. And so I've drawn the black triangle about the middle of my bar, and if the weights turn out to count equally, then that's the right place. The two arms are equal in length for two weights that pull down at the same amount. But if they're not equal, then you could make you could make the bar even by putting the fulcrum, by balancing the whole on some other point closer to one side or the other. If we put the fulcrum over there, that would mean that weight 1 was pulling down more heavily. And so the longer arm for weight 2 would make it balance, even though by this understanding, the weight 1 would have to be heavier. And it would take a class in physics to explain why the math is the same, but it is the same, that when you make the sides of the relative size of the two arms reflect the relative weights, then you will have something in balance. To give concrete terms, if these are in balance like this, and this part of the bar is, say, 1/4 the size of this, the longer one is 4 times longer, then you'd say, well, the whole bar is 5 units in length, and there's just 1 unit between the blue fulcrum and weight 1, which must therefore be heavier, and 4 units between the blue fulcrum and weight 2, which must therefore be lighter, and the difference in the weights must reflect the difference in the arms. That is, W1 must be 4 times heavier than W2, so that having 1/4 the leverage with its short arm would compensate for the W2 having the full amount, 4 times bigger leverage. We have the final average calculated at 84%, even though the two test results are 70% and 90%. So say, well, one thing we know, we know which test counts for more. It must be the one that stayed closer to the final average, that the 70 was able to pull the 90 down all the way down to 84, but not so far as the middle, 80. Whereas on the other hand, the 90 was able to pull the 70 up past 80, the midway point, past halfway toward 84. So just fill in a few details that we know and which will be useful. How big is this difference? Well, it seems to be 6%. That the low test score lowered the effect of the high test score by 6%. And what was the same number on the other side? How far up did the average go from the lower test score because of the influence of the higher test score? Well, that would be 14%. And then clearly we know the whole distance between them. We could add 14 and 6 together, or we could just subtract 70 from 90. The whole thing between the two is 6%. So it's 20% rather. So that we could think, well, okay, if it's true that the size of the change, the relative sizes of the change reflects the relative weights, what sort of calculation will let us understand that? We could say that this was, how much did the 70 lower the 90? Well, 6 out of 20 possible units. We know that the average is never going to be pulled down by the lower number so far that the average is even lower than the lowest number. That's not how averages work. And they say, well, okay, the higher number, how far did it pull up the lower number? Well, okay, so 14 out of 20. We could reduce the fractions to lowest terms if we want to understand them better. 6 over 20, what is that? Well, can divide both numbers by 2 and get 3 over 10, and now I've got a prime number in the top, so I know I can't reduce it anymore. That's not, but that's useful, as fractions in the lowest terms are helpful for many things, but really I could add a 0 to each one to add it, to multiply it by 10. That's what I'd like. So 30 over 100. It looks as though that the lower test pulled the higher one down by 30%. And if I think, well, the whole has got to be 100%, so what's left over, if I've identified 30% on one side, what's left over for the other side? Well, I would have to think 70 over 100, or 70%. Is 70% equivalent to the fraction of 14 over 20? Well, yes, it is. I multiply 20 by 5, I get 100. In order to keep the fraction equivalent, I would have to multiply the numerator, the number on top, by the same number. I multiply the number on the bottom. So if I multiply 20 by 5 to get 100, I should multiply 14 by 5. And what is 14 multiplied by 5? That's 70%. That seems to be the answer, and you could plug those answers back into the algebra method. If you prefer that algebra method, you could plug those numbers in and see if they represent a true solution to the problem.